So continuing on from the previous video, and we went through an example showing how by just changing the instance variable, we got a completely different result with our multiple threads. And probably at first glance, you'd think that it wasn't doing what it should be doing. So when I introduced terminology relating to threads, I briefly mentioned the heap, and that's the application's memory that all threads share. Now, I also said that every thread has a thread stack, and that's memory that only that thread can access. So in other words, thread 1 can't access thread 2's thread stack and vice versa. But they can both access the heap. Now, local variables are stored in the thread stack. That means that each thread has its own copy of a local variable. In contrast, the memory required to store an object's instance value is allocated on the heap. In other words, when multiple threads are working with the same object, they in fact share the same object or share that object. So they don't have their own copy as such, and so when one thread changes the value of one of the object's instance variables, the other threads will see the new value from that point forward. So how does that relate back to our application? Well, we're passing the same countdown object to both threads, and you saw that defined on line 8 and 10 on the screen. When we used a local variable for I, that was okay, because when the JVM allocated the space for the local variable, it used each thread's stack. Consequently, each thread had their own copy of I on their respective thread stacks. However, when we switched to using an instance variable, the JVM allocated the space for I when it created the countdown object, and it did so at that point on the heap. Now, threads share the heap. So in that case, or in this case, the two threads don't then have their own copy of the variable I. They in fact share the variable that's on the heap. So what that means is that when thread 1 executes and changes the value of I and then gets suspended so that thread 2 can execute, thread 2 will then see the new value of I as it has been updated from thread 1. It won't see the value of I that it had when it was last suspended. And that's why each thread is sometimes skipping a number and why numbers can appear out of order. So let's take a closer look at the output above in the screenshot that I've got there and try and make some sense of it. Now, we have to keep in mind that a for loop is actually several statements. And I'm talking about the for loop on line 36. The first time it's executed, it assigns the initial value to the variable. It then checks to see whether the for condition is met. If it is, the code within the loop is executed, and I'm sure you understand that because we've been using for loops throughout this course. But when we return to the for statement, it will then decrement I in this case and then check the condition again. So basically a for loop consists of several steps, and a thread can be suspended between each step. This is the key point I'm making here. So a thread can be suspended between steps. As an example, a thread could be suspended after the for has decremented the I variable, but before the condition has been checked again. Another example, it could also be suspended after executing all the code associated with the for loop, but before executing the print line. So let's, thinking about that, let's list out some potential suspension points here. So in the for loop, a thread could be suspended just before decrementing I, just before the condition, or just before printing out the value. So 3 spots there. And thinking about it, there's actually more suspension points than this because the println statement involves concatenation and IO and effectively calls multiple things. But this is really a good, really good enough understanding of what's happening. The point here is that there's multiple points where the current thread could be suspended. So when we analyze the output, all we can really be sure of is what the value of I was when each thread printed it at that point in time. So both threads thought the value of I was 10 the first time they executed the print statement. That means that thread 1 was suspended before it could decrement I from 10, in other words reducing it to 9, because when thread 2 printed the value, it still had the value of 10. Now when thread 1 gets the chance to print the line again, the value is 9. So from this we can guess that thread 1 decremented the value from 10 to 9. So how do we know that? Well, if thread 2 had beaten thread 1 to it and decremented the value from 10 to 9, when thread 1 had the chance to run again, it would have decremented the value from 9 to 8. So it would never have printed the value 9 at all. But because it does, we know that thread 1 decremented it. And by the same reasoning, we know that thread 1 was suspended before it could decrement the value from 9 to 8. Thread 2 then decrements the value from 9 to 8 and then prints 8. So the two threads go back and forth like this for a bit, with thread 1 decrementing the value, printing it and suspending, and then thread 2 decrementing the value, printing it and suspending. Now, rather than each thread being able to count down from 10 to 1, they keep skipping numbers because of the interference from the other thread. In fact, when problems arise because threads are interleaving and accessing the same resources, the situation has a name. It's known as thread interference. And we can see why it's called that now from what we've shown here on the screen. These two threads keep interfering with each other because whenever they get a chance to run, the other thread has changed the value of I, and as a result, each thread can no longer count down from 10 to 1 and hit all the numbers. We'll also see this situation referred to as a race condition, which is the more common term for when two or more threads are writing a shared resource. It is important to note that there wouldn't be a problem if both threads were only reading the shared resource. Problems will only arise when at least one of the threads is writing or updating the resource. So let's think about what might have happened when the numbers 2 and 3 were printed out of order. From the pattern we've seen before, we could guess that each thread was decrementing the value, checking the for condition, executing the print statement, and then suspending. So they're going back and forth, except when the numbers 4 and 2 were printed by thread 2. So we can guess from the output that the two threads still interleaved, but thread 1 didn't get a chance to print the value 3 before it was suspended. So you might wonder, why it printed the value 3 when it got the chance to run again. After all, wouldn't thread 1 have decremented the value to 2? So why didn't thread 1 print the value of 3? So in this case, our oversimplification of the possible suspension points don't work. Now, I mentioned that there are potential suspension points within the print statement itself, and that's what's actually happening here. So let's take a stab at how these threads are executed. Thread 2 prints the value of 4 and is then suspended. Thread 1, which has printed the value 5 previously and then suspended, decrements the value to 3. Thread 1 starts to execute the println statement. It builds the string that it's going to print, and at that point in time, the value of I is still 3. Thread 1 calls println and then is suspended while the println method is executing, but before the string is output to the console. Thread 2 decrements the value to 2 and prints it, and then it suspends. Thread 1 continues to execute the println method and prints out the string it created when the value of I was still 3, then suspends. Thread 2 decrements the value of I to 1, then prints it out. Now that the value of I is 1, both threads at this point exit the for loop and terminate. Now I know that is a bit of a mouthful or a little bit to get your head around, but you can see that every time we run this, we're going to get a different result, and there really is just no way to predict which thread is going to print out which numbers. And obviously in the case when I ran this previously, we've got a completely different result to my example image here. So hopefully you can see now that threads are deceptively simple to work with. We just have to create an object, subclass from thread, and call the start method, or create an instance of the thread class with a runnable object, which we've done in this section. But even when we have only two threads that are doing something, really simple, like in this case, you can see how problems can come about because object instances are stored in the heap, which is shared across threads in an application. So I'm going to finish the video here now. In the next video, we'll continue our discussion about race conditions. See you in the next video.